Hi guys, in this video we're going to look at what's called implicit differentiation. It doesn't come up very often on our course, and it will only really be found in the circle if they ask you to find the equation of a tangent or the slope of a tangent when we're using a circle. So I'll talk you through it, and then what we'll do is I'll go through an example. Okay, so the first thing I'm going to do is just go back to something we've already done, which is y is equal to root x. And we're happy that we can work out the derivative of this by changing it into its index form. We've done this plenty of times on the exercises, x to the half, and then what we do then is we bring down the power, rewrite the x, take one off the power, and then we can change it back into its fractional form. So it comes over 1 over 2x. Now you've done this loads of time, y is equal to root x. There's another way which is called implicit differentiation. And what we can do here is we can say, okay, so we have y is equal to root x. That's great. I'm going to square both sides, so I get y squared is equal to x. And then what I do, essentially, is I differentiate everything, left and right side. And the rule is, if I differentiate an x, then I just leave it as its normal differentiated form. But if I differentiate a non-x, I differentiate it as if it was an x, and then I put dy dx on the end. Okay, so first things first, let's have a look at y squared. If I pretended that this was an x squared we know would differentiate to 2x, but it's a y, so that's okay. So instead of going to 2x, this is going to go to 2y. But because the variable is not an x, we have to write dy dx after it. That's equal to, and let's have a look at this one here. So this x, okay, if we differentiate it, that goes to 1. And because it is the variable x, we just leave it as it is. Now hopefully you can see I have 2y dy dx is equal to 1. And I'm looking to try and get dy dx is equal to something, because I'm looking for the differential. So dy dx is equal to 1 over 2y, but I need to have this variable in terms of x. Well, I would like to, but hopefully you can see that y in our original equation here is equal to root x, so I can change the y for root x, and that now means I get dy dx is equal to 1 over 2 root x, which is exactly the same answer as we would have over here, doing it the methods that we've already discussed. So let's have a look at the sort of question you're going to get for this. So it says find dy dx for the circle with equation x squared plus y squared minus 2x plus 6y minus 3 is equal to 0. Hence find the slope of the tangent to the circle at the point 4 minus 1. Again, I've just written down here the sort of things that you need to do. So it says differentiate every term as normal. If the variable is not x, put dy dx after it. So let's do that. So I'm going to write it down. I've got x squared, plus y squared minus 2x plus 6y minus 3 is equal to 0. Okay, we'll look at the first one. So the first one is x squared, and that's going to differentiate to 2x. It's an x, so we don't have to do anything else with it. Going to look at the second one, which is a y squared. Okay, that's going to differentiate to 2y, but because it's not the variable x, we stick dy dx on the end of it. We then look at the minus 2x. That's nice and straightforward. That's going to differentiate to minus 2. And then we're going to look at the plus 6y, and that's going to differentiate to plus 6. But remember, that was the y function, so we have to put dy dx on the end of it. The minus 3 is fairly straightforward. It's a constant. That's just going to disappear. And then we have to look at the stuff on the right-hand side. And if we try to differentiate 0, 0 will become 0. Again, because it's a constant. So what we have here is 2x plus 2y dy dx minus 2 plus 6 dy dx. The next thing we try and do is we try and get all the dy dx's on one side and shunt across to the other side the non-dy dx terms. So what we have here is we have 2y dy dx plus 6 by dy dx is equal to minus 2x plus 2. So all we've done is we've thrown this one across to here, and we've thrown this one across to there as well. Next thing we're trying to do is we're trying to isolate dy dx. You can see it's in both terms here, so we're going to factorize it. So we take dy dx out, and that means what we have is we have 2y plus 6 is equal to minus 2x plus 2. So all I've done there is I've taken dy dx as a common factor, put it in front. So dy dx by 2y gives us this, dy dx by 6 gives us this, and the right hand side has not changed. I now have dy dx multiplied by this bracket. So in order to get the bracket on the other side, I'm going to divide both sides by 2y plus 6. And if I do that, I'm going to get dy dx on the left hand side is equal to minus 2x plus 2 all over 2y plus 6. So I now have the differential that I have done implicitly. Okay, so not quite finished. We've got to find the slope of the tangent to the circle at the point 4, minus 1. That's pretty straightforward. So at x is equal to 4, y is equal to minus 1. We throw it into this function here. So dy dx is equal to minus 2 by 4 plus 2 all over 2 by minus 1 plus 6. Work it out, that's minus 8 on the top plus 2, so that's minus 6. And then on the bottom we have minus 2 plus 6, which is 4. So that's equal to minus 3 over 2, and that's the slope.